In this presentation, we're going to discuss about assembly language programming and computer architecture. So understanding of basic computer architecture, introduction to x86 CPU architecture, then the instruction set of x86, and some examples and demos are the agenda for today. So why do we need to learn assembly language? So there are many reasons. One is better understanding of the output code generated by the compiler. So basically, compiler generate assembly language instructions. So to understand that better, you need to know assembly language. Understanding of different features in C like pointers, calling convention, etc. require the understanding of assembly language. So there are many other reasons like reverse engineering, debugging, optimizing the code, etc. So we are not completely targeting to program in assembly language, but we are mostly targeting to understand the assembly code generated by the compiler through this presentation. So the diagram shows basic computer architecture. So as you can see, we have CPU in the middle. So CPU is a computer chip which does processing, or the central processing unit, which is connected via something called buses or wires inside the motherboard to devices and the memory. So devices is here and the memory is here. So memory is again a chip. Devices are connected to bus controllers, which are also chips, or we call it chipset. So everything is plugged into one single board called motherboard in a PC. So the bottom line is CPU, which is executing the instructions or doing the actual job, is connected to memory and devices. CPU. As I mentioned, CPU is a chip in the motherboard. It is connected to devices and memory via buses and bus controllers. Buses are practically wires. CPU fetch and execute instruction from the memory. CPU registers. CPU contains small internal memory regions which are called registers. They are very small compared to the main memory and very fast compared to main memory. These small memory regions inside the CPU are called registers and are well defined for a particular make of CPU. So let's see the working in a nutshell. So programs are loaded into the main memory. CPU start executing it from the memory. CPU mostly does following three things: read data from memory or devices to some register, modify or process that data, write back that data to the memory or devices. So practically everything we see is one of these three things in a computer. Let's consider an example of adding two numbers. Suppose you have an application which add two numbers and display the output. So you type two input numbers in the keyboard. CPU read those two numbers from the keyboard into CPU register. That is a read operation. Add values in the register, modify or process, and the result is written into the video memory to display. So this is not exactly what happens, but this is sufficient for the purpose of explanation for the time being. So mainly CPU do processing in the values in registers due to performance reasons and not on the memory or device directly. So this is pretty much true for x86 Intel architecture. So registers are like wallet for a CPU, if you will. So wallet is what you use for immediate purchases. So the computer memory normally contains programs. So programs are nothing but binary data. So the binary information constitutes a program can be divided into mainly two types: code and data. So let's try to understand what is code and data. So code is a command to the CPU and instruct the CPU what to do with the data already given or going to give. So following is a simple example. Suppose a baby is CPU and following are the instructions given to the baby. So drink milk, smile, close eyes and go to sleep. So let's analyze the code and data in this. So code is drink, smile, close, go to. So all the verbs are code. All the nouns like milk, mouth, eyes, sleep are data. Note that mouth is implicit kind of data for smile, which is very common when it comes to real CPU. So far our discussion has been very generic and it was applicable to general computer science as well as any CPU for that matter. Now let us see Intel 32-bit CPU registers or Intel specific architecture. Rest of the presentation is going to stick with Intel 32-bit architecture or x86 architecture. So following are the list of registers which we need to concentrate. So there are other registers as well, but we won't be dealing with in this particular presentation. So as I mentioned, registers are small memory location inside the CPU. So following are the 32-bit registers inside the Intel x86 CPU. So EAX, EBX, ECX, EDX, ESI, EDI, EBP, ESP, EIP, and eFlags. So those are the registers we're going to discuss. So let's have an overview of each of them. So ESP and EIP are strictly special purpose, which means that this particular memory locations inside the CPU are used for very special purposes. ECX, ESI, EDI are occasional special purpose registers, but we can use for other purposes as well, depending upon the occasion. EAX, EBX, EBP, EDX are normally general purpose registers, although the use of EBP as a special purpose register is compiler dependent. So we will see what it means later. eFlags is also a special purpose register, but it is different from other registers from the fact that it is the bits inside the registers are being used than the register as a whole. So we will see the details later. So it is important to understand and remember the name of the registers and the use of them. So let's see a demo in Visual Studio in which we're gonna see all these registers for a Hello World C application. So this is just a simple Hello World application in Visual Studio. So I'm gonna start debugging. So I got a breakpoint here. So now what I'm gonna do is I'm gonna go to debug Windows registers. So here we can see all the registers we have seen so far. So EAX, EBX, ECX, EDX, ESI, etc. So these register values are the values of this program or this thread for that matter while the breakpoint was hit. So another thing we can do in Visual Studio is go to the disassembly window. So this is the assembly code generated for that particular program. So we will see this later. So in Visual Studio we can see both the assembly code as well as the registers. So now let's go back to our slides. So we have seen this demo, how to see registers and disassembly in Visual Studio. EAX, EBX, ECX, EDX, EIP, ESI, EDI, EBP, ESP and eFlags. So we have seen all these registers in Visual Studio. So in our exercises we will be mostly dealing with these registers. So registers and programming. So basically registers are the programmer visible part of the CPU. So from a programmer's standpoint, registers are CPU itself. All the programming language compilers or the compiler plus runtime for that matter create one way or the other the binary instruction to the CPU to which the program is targeted. All the programming language does that: Java, C#, JavaScript, C++, anything. Special purpose registers. I have mentioned that some of the registers are special purpose. What is the meaning of that? Certain instructions use some registers implicitly. In the example of the baby as CPU, for the instruction smile, the baby has to use the mouth. So that is an example of a special purpose register. Again, mouth can be used for eating as well. So it is not a strict special purpose register, which means that other action can be done with that memory location as well. So now let's consider the instruction here. So in this case, the baby has to use ear to do that operation. And normally we don't use ear for any other purposes. It is strictly for hearing. So it is a strict special purpose register. Now let's have a concrete discussion on special purpose registers. So EIP is the best example for special purpose register. So it's very strict. So EIP always point to the code, which is next instruction the CPU is going to execute. EIP points to nothing else. The full form of EIP is Extended Instruction Pointer. EIP controls the flow of the program in general. So it's like a steering of the car. So we have seen EIP register in Visual Studio, and I'm going to skip this demo. So now ESP, or the stack pointer. So normally a program has hundreds of instructions, if not thousands. So all program needs some temporary storage to keep track of the immediate state of variables, etc. For example, local variables or the arguments passed to a function. To manage that, program uses a small chunk of memory called stack. So stack is nothing but a small chunk of memory. So ESP register always point to the top of the stack. So there are certain instructions which are dependent on the ESP register, which is push, pop, and return. In normal cases, none of the compiler use ESP for any other purpose other than point to the stack of the thread. So it is a strict special purpose register. So I'm skipping this demo as well because we have seen all the registers so far. So now comes the eFlags register. So eFlag register is a register which has a lot of flags in it or bits in it. So basically this is the register where we look for the result of an operation. So set or create by result of operation like addition, subtraction, division, multiplication, any operation for that matter. So we will see the use of eFlags in general later. For the time being, what you should know is eFlag register is a register which has bits in it, unlike other registers which are the results of the operation which has performed before. So following are some of the flags which eFlags contain, which is a carry flag. So it's again a result of operation. Zero flag, if the operation result is 0, this 0 flag is set. Then the sign flag and the overflow flag. So eFlags contains other flags as well, but we will be concentrating only on the one we have just mentioned. We will do this demo after discussing the instructions. Now let's go into the instructions. MOV or move. This is one of the very basic x86 instructions. What it does is move data between memory and CPU register, or vice versa, or between CPU registers. So there are a lot of instructions which indirectly do what move does. Maybe in certain cases they are more efficient as well. Example like LEA, push, pop, etc. Now let's go to Visual Studio and see the assembly equivalent of a program which add two numbers. So this is a very simple C application which add two numbers. So we have two variables A and B, and sum of A and B is assigned to C. Now let's have a look at the disassembly of this. So for that I'm gonna start debugging. So if I go to debug, Windows, disassembly, I'll get the disassembly window. So now let's try to understand how to deal with disassembly window. So here you can see the void main. So for that, the generated assembly code is this 3 lines. Int a equal to 10 becomes this. And as you can see, the yellow arrow is pointing to this particular line, which means that my EIP is this particular value. For example, if I go to EIP, so that is exactly same as 00A21006. So that is the next instruction this program is going to execute. That is what the yellow arrow shows. So you can look at the source code if you like. So source code also has the same instruction pointing with the yellow arrow. So now if I look at the instruction, so the instruction which I'm going to execute is move dword ptr a 0ah. So now let's try to understand what that means. So dword ptr a, this is something you should get used to it. So what that means is you are going to save 0ah to a memory location of 4 bytes. So dword ptr means that it is a dword pointer. So a is a dword pointer. So it's not the value of a, but it is the address of a. So this is how the assembly representation of that. Why it is dword is because a is an integer and a is 32-bit. So this is a move instruction. For the move instruction, there will be 2 operands. One is the target. The first argument is the target, and the next argument is the source. So the arguments are separated by a comma. If I press F10, I will execute that instruction. Now the next instruction is very similar. I am passing 14 hex, which is 20, to B. If you look at EIP is red, which means that EIP is changing. So after every instruction, EIP is changing and it's pointing to the next instruction. So now in this case, I'm going to change EAX as well. So EAX is a register which contains this value at the moment. Now what I'm going to do is I'm going to copy whatever value A contains to EAX. So I'll shortly explain why we are doing that. So F10. Now if you carefully look at EAX, you can see that EAX is going to change. So EAX became 0A, which was the 0A we passed here, which contained in dword ptr A. So that value we have copied to EAX register. Now EAX contains 0A. If you look at here, it became red. Now I'm adding EAX and dword ptr B, which means that whatever value EAX contains, I'm adding to dword ptr B. So now I'm going to press F10 again. So now where is the result came? So result has gone into EAX itself. Result is 1E. So now the result is inside EAX, so which is 30. So now EAX became 30. So here EAX was 10. After this instruction, EAX was 10 or 0A in hex. Instruction here, we have added dword ptr B to EAX and EAX became 30. Now what the program is going to do is copy that EAX into C. So that's what we are saying here. Add A plus B and assign it to C. So those are the operations going on here. So this 3 instruction. So these instructions are generated by this statement. So that is called epilogue, and this is called prologue. We will see that shortly, what is a prologue and epilogue. So now let's go back to our slides. So following are some of the operations which a CPU support. One is add, which we have seen already. Another is subtraction, SUB, OR, and XOR, shift. All these operations are supported by CPU. Even CPU support multiplication, division, etc. So we have seen this example. So I would recommend you to write a program which does AND, XOR, OR, and see the assembly instruction generated as an exercise. So now we will see jump instructions. So there is a class of instructions which changes the value of EIP register. So jump instructions are a class of instructions which changes the EIP value, which means it changes the flow of execution. So there are many types of jump instruction based on all the flags we have discussed, like zero flag, carry flag. So we don't discuss all of them, but we will try to understand how jump works. Now let's go back to Visual Studio and see a jump instruction in play. So we have a program up here which has a simple if loop or if condition. So we're going to see the disassembly of this. So I'm going to start debugging. So this is my disassembly window. So before we analyze this program, I would like to point a couple of things. One is, if you really want to see the exact same output as what I'm seeing, you have to change your build to release. So here there's a drop down up here which has debug and release. You have to make it release. Also you have to go to properties, optimization, you have to select disable. By default it will be O2. You have to make it disable. Only if you do those two steps you will be able to see the exact same output as I'm seeing in Visual Studio 2010. I'm removing all the extra instructions which is there in the debug build, as well as I'm removing the compiler optimization. So I'll get a clean assembly without the debug instructions and optimization. Now my first instruction which we have seen is moving 20 to variable A. So 14 hex is 20 and I'm moving it to the dword ptr. Now as part of the implementation of this particular statement, this if condition, we have two instructions. One is a compare instruction and one is a jump instruction. So now let's see what compare does. What compare does is it subtract this value from this value. So which means that it subtract 10 from 20, which is the value of A. Compare instruction doesn't store the result anywhere, but it will change the flags. So let's see the flags in the Visual Studio register. So for that you have to right click and click flags. So these are my flags. So in this case I'm going to give special attention to zero flag. So that is only flag I'm interested in this case. So zero flag is currently set, or the zero flag is currently 1 in this particular case. So now I'm going to execute the move, press F10. So zero flag is still 1, no one has changed the zero flag. Now I'm going to execute the compare instruction. So which means that if the subtraction is ending up in 0, the 0 flag will be 1. Otherwise, if the subtraction result is not 0 or some other value, the 0 flag will become 0. So in this case, we are expecting the 0 flag to be changed to 0. Yep, that happened. Our 0 flag became 0, which means that our operation, the result of the subtraction we have done here using the compare instruction is not 0, which means that A is not equal to 10. So this jump instruction is called jump not equal to, which means the jump instruction will be successful, or the jump will happen if the 0 flag is 0 or the 0 flag is not set. So where we are jumping, so this is the jumping address. So if you look carefully, we can see that this is that address. So we are skipping one instruction here. So that was the instruction which was supposed to set A equal to 100. So that is not going to happen because we are going to jump to this particular location here. So this XOR instruction is going to get executed, which is the function epilogue. So once again, we did comparison between A, which is equal to 20, and 10, which is equal to 0A. We did the comparison. Then the result of the comparison is not equal to 0. Now we are doing a jump instruction which depends on this particular flag. So this JNE will become success if 0 flag equal to 0. So this is not equal to 10. So we are not going to execute this particular statement and we are going to jump here. So after the execution of this particular statement, what will happen is our EIP will change to this particular value. Let's see that. So I'm going to press F10. So that is exactly what happened. My EIP got changed to this value because my 0 flag is not set, which means set not equal. So I'm not executing this instruction or equivalent this instruction. So jump instructions depends on one of these flags. So there is an unconditional jump instruction called JMP which doesn't depend on any of this flag. Otherwise, all the jump instructions depend on one of these flags. So we have seen the mechanism of how normally jump instructions work. Now let's go back to our slides. Now let us see a couple of instructions which are related to function call in C. Currently we're gonna see push, pop, and read. So these instructions implicitly uses stack. Push is similar to a move instructions in which stack pointer is involved. Pop is the opposite of push. Read is just like a jump instruction based on stack pointer. So one related instruction is call. So call is again like a jump instruction, but it uses stack. Call is the instructions which we use for function calls. So it is very similar to jump instruction with additional actions on stack. So we will see all this for instruction push, pop, read, and call in a demo. So we have a little program here which add two numbers, and we're gonna look at the disassembly of that. So we have a function call up here which adds two numbers. So I have a breakpoint up here and I'm going to start debugging. So now let's look at the disassembly of this program. So we have a couple of push instructions and call instructions, etc. here. So these two instructions I'm going to explain at the end, as well as this. So currently concentrating on the push instruction here and what it's going to do. So basically push instruction is going to push or copy that 14H into the stack, or the memory where stack is pointing to. So let's see where stack is currently pointing to. Currently the stack is pointing to this particular location in the memory. So what that means is, so if I type ESP here, these are the values in the stack at the moment. So now what I'm going to do is I'm going to find out what are the next two D words in the stack. So for that I have to subtract 4 bytes from the current stack pointer. Why I am subtracting is because in x86 platform stack grows downwards. If the stack was going upwards, I would have added 4. In this case stack grows downwards, so I am subtracting 4. So minus 4. So I got this value, Control C, Control V. I have two push instructions, going to subtract 4 once again, minus 4, got this. So I got the next two D words after stack pointer in the stack. Those are the next two D words. So what this push instruction is going to do is, it is going to copy 14H to the first D word and 0A to the second D word. We can see 7C up to 7C. I'm going to put this C as 0, enter, because we want to see 8 and 4. I'm reducing a little bit so that D words are clear, so each D word is visible. So this is 7 8 and 7 4, which we are going to copy after the push instruction. So I am expecting 7 8 to be 14 after pressing F10. Also one more change is I'm going to decrement the stack pointer to that particular value, which is 7 8. So stack pointer is going to become 7 8, and 7 8 is going to contain 0 1 4. Let's see that. I'm going to press F10. So that is exactly what happened. Stack pointer became 7 8 and this contain 1400. Now you must be guessing what is going to happen next. It's very simple. Similarly, stack pointer is going to become 7 4 because I'm going to decrement the stack pointer and I'm going to copy 0A to this particular D word. So I'm pressing F10 again. So same thing happened. Now let us discuss the call instruction. So the call instruction does two things. One is changing the EIP to this particular value to change the code path. Copy the next instruction, the address of next instruction onto the stack. So currently the stack is pointing to this particular value, so which is this. So this particular value is going to be this address, which is the next instruction after call, and EIP is going to be this particular value. One thing we have to remember is to see this, you have to press F11, otherwise the call will return. So what I'm going to do is I'm going to press F11. So EIP and stack I'm expecting to change. F11. So let's see what is the value of EIP. So EIP has changed, and this also has changed. So EIP should be this. Yes, EIP is that value. That is correct. Now let's verify this. So 1C 10 EC 00 is the memory representation of this particular devote. So which means that this particular value is pushed onto the stack by the call instruction. This particular address is also called return address. This is how the RET instruction, which we are going to discuss, going to come back to the calling function from the callee. So this is called return address. So return address is set by the call instruction. So now coming back, so we are seeing the same instruction pattern which we have seen in the main, which is push EBP, move EBP comma ESP. Now it's a good time to explain that. So this is called function prolog. So this is doing nothing but saving the EBP pointer. So we are going to use EBP pointer for something else. So pushing the EBP pointer to the stack. This is done mainly for two purposes. One is easily access the parameters passed and the stack arguments or the local variables. Another big advantage of EBP is debugging. So when you debug, it's very easy to figure out what are the variables on the stack and what are the arguments passed on the stack using the EBP. So it is not mandatory that you save EBP always, but it is always good to have EBP saved on the stack. Certain calling convention like x64 calling convention, fast calling convention doesn't save EBP on the stack. So in our case we are saving EBP, pushing EBP to the stack and using EBP after it, like this. In this case I'm copying ESP to EBP, which means that I'm going to access the local variable etc. using EBP. If I look at the end of the function, I can see that I'm popping EBP, which is the exact opposite operation which I'm doing here. So here I am saving EBP to the stack. Here I am saving it back to the register from the stack. So this is the opposite operation. So this is from the memory, from the stack memory to the register. This is from the register to memory, which is stack. Inside the function, what I'm doing is I'm moving this pointer, which is A, to EAX. Then I'm adding whatever value in EAX plus B, whatever value in B. So I'm keeping the result in EAX itself. So EAX is the place where the calling function look for the return value. So that is another important point. So return value is always in EAX in x86 calling convention in Windows. So now the last thing which I have not explained is a RET instruction. So RET instruction is nothing but it will change the EIP to this particular value. So after this pop instruction, the stack will be here. RET instruction does nothing but change the EIP to this particular value, which is the return address, which the call instruction saved onto the stack. Now let's see the execution. So I'm again pushing EBP to the stack. So the stack pointer going to change. So stack pointer change again 4 bytes. I'm moving ESP to EBP to access the local variables and things like that. In this we don't have much of a local variable, but we have the arguments passed. Then I'm moving A to EX for the addition operation. Now I'm doing the actual additional operation. So currently 1E, which is 30, we have in the EAX, which is a sum of 20 and 10. Now we have the pop up here. So if you look at stack, the stack is going to go in the opposite direction. After this instruction, the stack going to be 7 0. So F10. So stack became 7 0. The stack is pointing up here, and this is the return address. Our EIP is going to change to that particular value. So F10. So EIP is changed to that particular value. Also the stack pointer changed. So RET is exactly opposite to the call instruction. We have reached here and our stack pointer is back to the exact same value before the call instruction. And now we are adding ESP8. The reason why we are adding 8 to ESP is to reverse these two instructions. We could have done pop, but there is no point. We are not going to use this value anymore. So what we are going to do is we are going to discard that value. So to discard that value, we are going to add ESP8. We subtracted 8 here, if you remember. So we are going to add 8 to reverse what we have done here. Now we have the EX contain 30. So we have an XOR up here just to make sure that our EX is cleaned up. Now we are going to do the opposite of what we have done before, the prologue, and this is also called the function epilogue. So now let's go back to our slides. So we have seen push, pop, RET and call instruction. We have also seen function prologue and epilogue. All our discussion pretty much were x86 specific as well as Windows specific. Now let us see something called calling convention in C. So calling convention decides how the arguments are passed to the stack of the callee. Who is cleaning up the stack? So we have C calling convention, standard calling convention, and other calling convention like this call, fast call, x64, etc. It all depends on the compiler. So calling convention is a compiler dependent entity. In the calling convention, the caller and the callee. So there are two functions. One is the caller and the callee, which is being called, should follow the calling convention. Otherwise, there will be stack eruption. Normally, programmers don't have to bother about calling convention. But if you get a function pointer from somewhere, and if you're calling that function from that function pointer, you need to know the calling convention of that particular function pointer. Otherwise, you'll be corrupting the stack. So we're going to see a little bit detail on C calling convention and STD calling convention. So let's see a demo. Let's try to understand what is C calling convention and STD calling convention. After that, we will see some of the difference between both type of calling conventions. So we have again the same application. So this time we have sum1 and sum2. One is standard calling convention, which is Windows specific, and C declare calling convention, which is a C calling convention. What we can do is we can go ahead to the assembly and straight away understand the difference. So if you execute the function, you don't understand the difference. Only if you look at the assembly, you will understand the difference. Let's go to the assembly code of this. I'm going to start debugging. I have a breakpoint up here. So I'm going to disassembly. So this is a main. So let's try to understand the difference in the way caller behaves. We are pushing two arguments as we have seen before, 14 and 0a, and calling the function. After that, we are not doing anything. So caller is very much simple. Let's try to understand sum2, which is C declare calling convention. So in that case, we are pushing, and at the end we are doing an add instruction. So this is one of the difference. So in this case, the caller is reversing the push instructions, or the caller is cleaning up the stack in the case of serial calling convention. So obviously someone has to clean up the stack here in the case of standard calling convention. So in the case of standard calling convention, the callee is going to clean up the stack, or the function which is being called is going to clean up the stack. So let's see that. Let's go ahead and look at the assembly of the functions. So I'm going to press F11. So this is sum 1. So we have the function prolog, no difference. Then we have the addition we have seen before, and we have the pop here, which is the reverse of function prolog. So now we have, instead of RET, we have RET8. So here is a difference. So RET8 is going to decrement your stack pointer. So this 8 here is the equivalent of add ESP8 in the serial calling convention we have seen in the caller. So that is done in the callee. So this is where we're going to clean up the stack. Callee is going to clean up the stack. Let's check the serial equivalent of that. So we don't have anything. So it is empty, just return. So in the serial calling convention, callee knows that the caller is going to clean up the stack. So it is not cleaning up the stack. So there are certain implications for this, which we're going to see next in our slides. So going back to our slides. As we have seen, the caller clean up the stack and the caller manages the stack. In standard calling convention, callee clean up the stack and callee manages the stack. So C calling conventions support variable number of argument like printf. Printf is a variable number of argument function. So for that kind of functions we need to use serial calling convention or C calling convention. C calling convention will increase the size of binary. For example, if you're calling the second function sum2 in our sample, if you're calling it 100 times, you will generate 100 times the add instruction, which we have seen later. The add ESP, 8 will see that instruction 100 times if you are calling that function 100 times. But in the case of standard calling convention, we will see only RET8 once, because that is in the callee, not in the caller. So standard calling convention, small binary, we cannot use for variable number of arguments. Being said that, I'm winding up our discussion with assembly. I think we have discussed enough assembly for us to go forward. One of the things I would like you to do is look at the assembly code of the program which we have written so far, or you are going to write. Always have a look at the assembly code as well to understand the code generation. When you look at the assembly code, if you see a new instruction, look in the Intel manual what that instruction does and try to understand that instruction. We have not discussed all the instruction of the x86, but we have discussed only the important ones. As I mentioned in the beginning of this presentation, assembly language is very much essential to understand C programming correctly. And that's it. Thank you very much.